So let's jump right into this. So, on August 6th, we, restarted the Beanstalk protocol. And when we restarted the Beanstalk protocol, we introduced a new feature, called the farm. The farm essentially being a, function that allows you to call multiple Beanstalk functions in one transaction. And, this was, it's proven to be, very popular and, used frequently on our website. Was trying to get some numbers revolving around how many percent of function calls are farm function calls. Wasn't able to compute it quite yet, but it's quite high. So kind of we want to be able to take, what we've done with the farm, and, it's proven to be a successful experiment, and we want to try to expand it to be as generalized as possible. And, essentially the goal here is to be able to do anything within DeFi in one transaction. And when we initially implemented the farm, we did so in a way that protocols were added on a protocol by protocol basis through pipelines. We introduced the Curve pipeline, which was a wrapper around the Curve protocol that allowed farmers to use the Curve protocol through the farm. And this was, it worked, and, the Curve pipeline is used frequently on our website. It allows users to swap from Ether into Beans, which is a multi-pool hop transaction, and then deposit those Beans, or add to a liquidity pool and then deposit the LP tokens, which farmers have loved. There's clearly a desire, for farmers to want to be able to use other protocols through the farm function to allow for a better user experience throughout all of DeFi. And the problem with the pipelines as we've implemented them today is that they require a full, wrapper pipeline contract to be written, audited, and upgraded through protocol governance. So what we've tried to do is create a way to allow any smart contract code execution to happen in a closed and secure environment outside of the Beanstalk protocol, such that we can make permissionless function calls to any protocol without having any of the assets within Beanstalk at risk. And so that's what the pipeline is. And along the process, we came up with a new type of way to share call data between function calls. Currently one problem with the farm function is all of the call data is a direct input from the user, which means that we can't read any on-chain values and input them into subsequent transactions. The most common application of wanting to be able to do this is when we perform a swap and deposit. If we want to swap 100 USDC into 100 Beans and then deposit 100 Beans, and let's say we want to do that. And on the swap, we're willing to take 1% slippage. So that means when we swap the 100 USDC for Beans, we're going to get somewhere between 900 and 100. But, it's unclear how much we're actually going to get. So this becomes a problem when we go to the second function, the deposit function, because the deposit function doesn't know how many Beans are going to be bought from the swap. So we introduced this internal intolerant mode, which basically says if the amount that you actually have is less than the amount you want, just use the amount that you have. And it's proven to be a potential security vulnerability throughout, the initial audit Halborn had and the follow-up audit, where they reviewed the code that was changed between the initial audit and the replan of Beanstalk, which led to the removal of the chop function. And it was recommended that we remove this mode. So we came up with this way to take a return value from another function and input it into a following function. So instead of using the internal tolerant mode, we can take the return value of the swap and then use the return value of the swap in the deposit function. And we've also applied this to the pipeline, so we can do the same thing in the pipeline. And then finally is, the third thing is a smaller thing, which is just, a couple lines of code that we tagged on, and that's we don't want users to have to do 2 transactions for an approval in a subsequent deposit. Say you want to deposit Beans. Currently, you have to approve Beanstalk to use your Beans and then call deposit. We want farmers to be able to call the ERC20 permit function directly through Beanstalk, so they can call a farm function with the permit call and then the deposit call following, so they don't have to make a separate approval call. So we can just jump into, maybe we'll start off with the pipeline first. So the pipeline basically provides, an interface to other DeFi protocols through Beanstalk. And we talked a little bit about this. There's a little more details here, but pretty much pipeline is a separate contract from the Beanstalk protocol that is just deployed separately and stored as an address in Beanstalk. And pipeline basically allows people to input a function call or a list of function calls, which pipeline then performs. And this allows us to allow these function calls to be at any address, at any function selector, because the pipeline isn't storing any value other than value that is intended to be used through the pipeline. So we'll walk through how we have architected that here. So basically there's the depot facet, which wraps the pipe. So, I guess maybe we'll start with the pipeline contract. So the pipeline, has three different function calls. One is just the pipe, the multi-pipe, and the advanced pipe. And the pipeline itself, oh my gosh, I can't type right now. This one. So the pipeline itself has, the pipe function, and then there's the, which pretty much just performs a function call on a given address with a given data and a given value, and then it checks the return to make sure it was successful. We have a subsequent version for memory, which is used in the advanced pipe, but pretty much the point is that people make function calls to pipeline, or they send function calls to pipeline, which pipeline then performs and returns the result. And then on top of pipeline, we have the depot facet, which this is a part of Beanstalk, and it pretty much just performs calls to pipeline. So kind of the way this works here is, one would not call pipeline directly, they would only call pipeline through a farm function. So the way you would do that is you would call a farm function that first moves some assets into pipeline through the transfer tokens function, or you could do deposits or plots. So you move beans, basically I say I want to transfer beans from my internal balance to pipeline in the first function call. And now there are beans in pipeline. Then we perform a function call to pipeline through the pipe or the multi-pipe or the advanced pipe function, which can do anything. That can be a swap on curve. And maybe we swap beans for USDC on curve. And then the pipeline, so we do a multi-call with two different functions where, it swaps on curve and then sends the beans back to my internal balance in Beanstalk. So we can see, down here, we have some examples where, we could transfer, say we want to, we have AUSD, Aave wrapped USDC, and we want to get deposited beans. The way we could do this is we could transfer the tokens from our wallet to pipeline. Then we could call the pipe multi-function in the farm with three subsequent functions. One redeems the AUSD, for USDC. So first we put AUSDC into pipeline. Then we redeem that for USDC, and then that USDC is still in pipeline. And then pipeline swaps that USDC for bean, and then that bean also goes back to the pipeline. And then Beanstalk, and then the pipeline calls Beanstalk to transfer the beans to the farmer's internal balance. And so now the farmer has gone from having AUSDC in their external balance to bean in their internal balance through this pipeline call. And then they can just deposit the beans from their internal balance. So, there's, a few other examples here in documents showing, how pipeline works and how kind of the farmer calls the farm to call facets, and then the depot to the pipeline to other contracts. So then, we have the depot facet as we walk through, which is kind of, has some functions that just wrap the pipeline to perform the function calls as we see here. And then, I guess, So the changes to the farm facet are very simple. Basically, we just added this advanced farm function, which uses these advanced function calls, which we'll get into in a second, because a lot of the logic is shared between pipeline and farm because they use these same calls. And then we have the basic just permit ERC20 token function, which is it's in here, which basically just calls the permit function on an ERC20 token, which we can just use in farm functions. So now to get into the advanced function calls, because this is where it gets a little bit confusing, but pretty much everything is based around the ability to basically take, say we have some data that is the return value from a previous function call. And this data can contain anything, but it's just some data. And then we have another function call we want to call. And that function call has, the data that we perform the function call on. So if we look, like at the function call as it's performed in pipeline, we basically function calls just, are performed on some bytes. We have a call data version just for gas efficiency, but when we copy the bytes, we have to use memory. So we call this memory version. And basically there's a return value, which is bytes memory. And then there's the call data, which is bytes memory. So basically what we can do is we eventually get our way down into this paste bytes 32 function, which can just take in some copy data, some paste data, and then an index, which is just a bytes index from where to copy from, and a paste index from where to copy to. And it just performs an mstore operation on the copy index, to basically copy up to 32 bytes to this function. So what is an example of where this is used? So say we have a farm function call where we call the balance of a user's balance. What is my internal balance of this token? And then it returns a value. We can then basically copy the return value bytes into the deposit function to make sure to basically handle any potential slippage. And we can do that through basically encoding it in the advanced advanced data payload. So basically everything routes through this this advanced basically these advanced bytes, which is some basically it's some encoded amounts of bytes that signal something. So first we have a type. The type is the type of advanced function call we want to make. And basically the goal is to be able to call this function, or we can call a list of advanced function calls that may or may not require any return data from other functions, but they can. We have our basic versions here where we don't need return data, where we don't copy any return data just for gas efficiency purposes. But technically every type of function can be called through the advanced pipe because we want full compatibility for users who want to be able to copy some functions from others and not. So the first type is basically a basic pipe, which is just a function call, no call data copy. Whatever call data the user inputs gets called. The type 1 is a single copy. We want to copy one value from a previous return value from a function into this function data. And then we have a type 2 for if we want to do a list of them. Say we want to send beans to the owner of the beanstalk contract. We could call beanstalk.owner and then beanstalk.balance of, and then transfer beans to the result of the owner function and the result of the balance function. And we could copy two return values into a single function if we wanted. And most of the time we imagine only this one will be used, but just as we think about future iterations of where we want Beanstalk to go, we think it's very important to, be able to support everything users can be able to want to do, so we never have to, modify this again. We have this, and then, so the first byte, which is just the type. And the reason we use bytes is because we want to minimize the call data size of the advanced data payload. And normally, when you take in inputs, if we put 1 byte as a call data, if we do it like this, it takes up a full 32 bytes of call data because it doesn't pack call data. or at least so we believe. And thus we found that we have to like manually encode bytes to shrink it into smaller sizes if we want the call data to be small. So something like a type where we only need 1 byte, we don't want call data to have to take a full 32 bytes, because it'll cost more gas. So we want to store it as 1 byte. And then we have a second variable here for padding. So this is used in the pipeline version of the advanced call to, basically the pipeline, sometimes we, and apologize. I mean, I guess I should stop maybe and take a second. Is everything okay? Any questions? Anything I should go back to before continuing? Is this too in depth? Not just do a quick gauge of where we're at.
It's so good for me so far. Obviously, I will have to look at the code because it's quite complex, this part. But yeah, you can go on. I am following very well.
Okay, thank you very much, and appreciate that. Okay, so the advanced data is called in 2 places: in the advanced farm function and the advanced pipe. So if we compare the advanced farm to the advanced pipe, there's one difference, or I guess we need to go to it's called from the pipeline itself, and that's basically that's in the pipeline. We have to each individual function call, if we want to use Ether in the transaction, we have to have some Ether value to be able to send as the actual value instead of including in the call data. So every function call takes 3 things: the address, the data, and the value. So what we need to, so if we want the advanced pipeline to be able to use Ether, we need to, in the advanced pipe, also encode in an Ether value if we want to allow the advanced data to use that. With the farm function, all functions in Beanstalk that use Ether have a specific value in the function signature so that so that it knows how much Ether to use. And then all functions either return the remaining if the value is different. So with the advanced farm, we don't have to be able to use Ether in the way we have to for the pipeline. So basically in the bytes, if we go back to the bytes, this padding is used in pipeline, as the send Ether flag. So it basically is either it's either 0 or 1, depending on whether in the pipeline you should send Ether or you shouldn't send Ether. So in the farm function, this byte is just padding, and it doesn't matter for as far as the advanced call data is concerned, but it's relevant for the pipeline to see if we want to send Ether. And then also specific to the pipeline is if the send Ether flag is 1, well, the last 32 bytes will be the Ether value. So if we go look at the pipeline, we have this function get Ether value, which checks if the first byte of advanced data is 0, it returns 0. If not, then we basically load the last 32 bytes of the call data, and that eventually gets plugged in as the value in the advanced pipe. So that's specific to the pipeline, but basically the advanced call data function processes the 2 types that aren't 0. The basic function call, we handle in the advanced farm function itself here, and in the pipeline advanced function itself, so that we can use the farm function that uses call data, and same thing here, instead of the one that uses memory. When we build the advanced data, because we have to paste data into the call data, we have to transition it into memory, which using memory is slightly more expensive from a gas perspective. So if we don't have to do any copying, we just want to be able to call the farm function with the call data itself instead of the memory. So we've separated that logic out into the actual, advanced pipe and advanced farm itself. And then, types 1 and 2 that perform copies, go through the memory version of the version that uses memory after we build the advanced call data. So if we jump into the advanced call data, let's look at how this works. So the advanced call data takes in every time the advanced pipe calls a function, it basically calls the underscore advanced pipe. Advanced pipe loops and farm performs the same. So they're pretty much corollary, except for this ether value thing. So we loop through each advanced pipe, and for each advanced pipe, we check if the versions, if the type is 0, a normal pipe call. Otherwise, we perform, on each transaction, the build advanced call data function. So the build advanced call data function takes in, the call data of the transaction that's about to be called. So the next transaction. So if we want to call a deposit function on the return value of balance of, this would be the deposit. And then we have the advanced data, which is, the advanced data is detailed here in the functions.js file. We have, an encoded advanced data function that, has some instructions on, how this works. And this basically, you give it the type, the value, and the copy data parameters, and it will, basically can, encode the bytes. So that is what it is, the advanced data, and advanced data is used in both the farm and pipeline. So the advanced data, is what either, which has the type and the type data. So the type data is, if the type data is 0, or if the type is 0, then I'm trying to see if this is broken down anywhere, but if the type is 0, then we're performing a basic call, so the type data is 0 bytes long. There's no type data. If we're using type 1, the next 30 bytes after byte 1 and byte 2 are copy params. And so if we look at copy params uses the last 30 bytes of a 32 byte slot to break it down into 10 separate bytes. So basically, the first 2 bytes are irrelevant. In the case of the single type copy, the first 2 bytes are type ID, and the first 2 bytes are these bytes, and then the next 30 bytes are copy params. So where in the case of n bytes, the first 2 bytes are type and padding, and then we don't bother to do any advanced encoding here. We just pad it with 30 more bytes. So pretty much everything but the first 32 bytes are a list of copy params. So it's very easy to decode. So if we look at how we decode this, copy params is just the first 32 bytes in advanced data, where if type equals 2, we skip the first 32 bytes. This gets stored as nothing, and then everything after that gets stored in copy params. So this is how we decode it, where we always use the first, regardless of which one it is, as the type. And here we always use the second, regardless of what type we are, the second index as whether we use ethers, only for the pipeline. So the paste advanced bytes, pretty much, or I guess we're still up here. And then the return data is the list of the return data of every function. So we just create this results array, when we start the advanced pipe and the advanced farm function, and it's just every time we perform a pipe call, we just store it in the results array. And we pass that into the advanced pipe, which gets passed into the build advanced call data. So, and then gets passed into the paste advanced bytes function. So the paste advanced function pastes bytes from the history of return values so far in either this pipe call or this farm function call. And then here, as we said, it's the call data of the next function and then some copy parameters. And the copy parameters are either 1, or there's a list of them in the case where type equals 2 that we just process one at a time. So that brings us into the paste advanced bytes function. So the paste advanced bytes first isolates the return data index by just shifting to remove the first 2 bytes and then shifting all the way back. And then we take that index of the return data. So if we're on the third function call and we, or let's go back to the case where we did a balance of and maybe then a transfer. In the 0th function call, because this is 0 indexed, we did a balance of function and it returned this value. So when we're in the first function call, we want to copy from the result of the 0th function call. So return data index would be 0. So when we take the bytes out of return data, we take the bytes that are returned by the balance of function. So this is the index of the return data, which we want to copy from. The next 10 bytes are the index within this data that we are going to start copying from. So, in all, of these bytes, the first 32 bytes is the length. So if we did a balance of function, we'd want to start copying from the 32, from the 32nd byte, which I think we've written up somewhere in here, here. So like if we want to, if we call the balance of function returns one value. So what the call data looks like, or so from our experience has been, is that the first 32 bytes are the size, which is 1, and then the second 32 bytes are the actual value. And so if we want to copy the actual value, we start from 32. But pretty much we, isolate these 10 bytes by shifting 12 to the left and then shifting back, all the way to the right. And we isolate the paste index. The paste index is the index in the call data that we want to start pasting the 32 bytes at. So the call data is structured where the first 32 bytes are the length of the call data, or the length of the call data, and the next 4 bytes are the function selector. So if we want to paste that the first parameter into the function selector, we would use 36. So if we were doing a deposit, and the deposit function in Beanstalk takes in first a token and then an amount, we'd want to use paste index equals 64 because we have 32 bytes for the length of the call data, 4 bytes for the function selector, and then we want to paste into the second parameter, so another 32 bytes, which brings us to 68. It's a little bit more confusing to use this kind of byte system as opposed to maybe using like 0, 1, or 2 and then just setting that equal to 32, or 32 plus 4. But we don't want to make any assumptions about what kind of functionality people want to use. Maybe someone wants to overwrite a function selector, and thus we should let people be able to do that in their function call, because they're the ones calling it. The contract itself doesn't have to know anything about the structure of the data, because the user is inputting these kind of paste and copy indexes, and if the user makes a mistake and puts in a wrong copy or paste index, that's their fault. They should know the structure of the call data such that they know how to properly copy and paste, from previous return values. So this basically just calls by, it isolates each 3 of these parameters and then just performs the 32 byte copy and paste. So that's about it. Pretty much to summarize against the events pipe again, we just perform a list of function calls where we take the results of all the function calls and perform either 0, 1, or n copy operations from previous return values on the function calls. And then, in the case of the pipeline, we also have the ability to send ether. Most of the time, we're not going to send ether. It's going to be rare, and can't really think of a case where we would use more than one, non-zero ether value very frequently. But who knows? Maybe there will be a reason, and we don't want to, have to add this functionality later when we find it's relevant. So, we just want one way through the pipeline to do anything with these function calls. So, that's kind of, how this came to be. So, that's pretty much everything. Thank you guys for listening. Anyone have any questions?
No questions on my side. I am checking the documentation and it's very well written. So I have everything there. And with this video, I think that we'll have everything for the audit.
Thank you so much. Appreciate it. I'm glad to hear that, really tried to make sure you guys had everything this time. And, if anything's missing or anything's unclear, please, always feel free to reach out. And, we always, want to be here to help you guys as much as possible, because we know it's not, it's not always clear to figure out what stuff is supposed to do.
Definitely.